talked about specification limits. And we will now talk about an example and see how we can compare two processes and get a criterion that distinguishes whether one process is better or the other with respect to meeting the specification limit. So in an assembly plant, a number of output characteristics related to wheel and alignment are measured on a car. And we're interested in the pull of a car. The pull measures the tendency of a car to turn on a straight surface if the driver's hands are removed from the steering wheel. You may have experienced that, hopefully not. I had an old car some 20 years ago, my first car, and that always went a little bit to the right on the highway, and so that wasn't good. The specification here for pull are some values. Well, we don't know the metrics, but these are the values that were given. 0.23 plus minus 0.25. So it's even, we have an upper and lower specification limit based on this, right? And the vehicles that don't meet the specification limits have to be taken off the assembly for repair. And so that costs money. So ideally, we want to have a process that doesn't let that happen, or only lets it happen very rarely. We have data for 400 vehicles, and they are plotted here. Because we like looking at graphs, I've plotted the same data both as a histogram and as a run chart over here with the specification limits. Now, the limits are the same, just below 0 here and below 0.5, the same on this side. And we see there's one time we're outside, here one time we're outside, but more or less looks like it's in control, right? In control means not going up, not going down, not doing some funky curve thing. It's just chugging along. So then the question is, how much variation is there? Well, I mean, this looks pretty good. We have only one issue here. Less is better, but is this good enough for a regular process? We don't know. Well, we need to measure something. And one way of measuring how good the process is the capability ratio. The capability ratio is defined as follows, where we have the estimated mean and the estimated sigma. We have the upper specification limit and the lower specification limit. This index pk is used in the books, but it's unexplained. I cannot tell you where it comes from. If somebody finds out, let me know. I'm just using the same index that the books also use. This applies for a continuous outcome. And we have to remember that these specification limits are targets, right? This is an externally imposed target. It's not a confidence interval. All right, what does this measure? It measures the distance between the process mean and the nearest specification limit. And it's the nearest because we're looking at the minimum up here. And the distance is measured in units of 3 standard deviation. So a distance of 1 means I'm 3 standard deviations away. And larger is better, right? Ideally, I want the estimated mean as far away from the specification limits as possible, where I'm farther away in the sense that if I have less variation, then I'm farther away. So larger values are better. Choosing the minimum up here allows basically for a non-center distribution. And if I had a center distribution, I would only need one of them here. If the process exhibits little variation, then the ratio is larger. Okay, that makes sense. So for this particular example, we have estimated a mu of 0.277 and a sigma of 0.062. We plug that into the formula where we have the mu here twice, and then we have the upper limit, the lower limit, and then 3 times sigma at the bottom, and we get 1.09. So we know 1 would be 3 sigma, 1.09 is a little larger than 3 sigma. Is that good enough? Well, one of the influential researchers or gurus in this area is Montgomery. And he gave the following guidelines. For an existing process that where you have something already working and you don't want to change it unless you have to, he suggests 1.33 is good enough or larger. If you want a new process, you want to do it right? And you have to change it anyways. So you're suggesting 1.5 is good. A safety critical process is 1.67 or larger. And a Six Sigma quality process is 2. Now, why 2? Well, because 1 means 3 sigma, so 2 means 6 sigma. So the 6 sigma goes along with the 2. That makes sense. But why do we measure it at all? Well, it's because 6 sigma is a thing. GEE, that large company in New York, and in all kinds of states in the US, they came up with this, and they wanted really high quality products. We're now talking, 40 years ago. And they said, we want extra high standards. We want our processes to be 6 sigma quality processes. And you can actually get, I think, a 6 sigma belt, and they have all kinds of 6 sigma training. So 6 sigma is a big thing in that. Okay, so from our data, we had 1.09 for an existing process. And based on Montgomery then, that wouldn't be good enough. What would you do? Well, you would troubleshoot the wheel alignment process and try to improve it somehow. This is where you get to have fun with the engineers on the floor, and that's the part that we can't do in the classroom. What you wouldn't do is tell the workers to try harder or to be extra careful, because that wouldn't do anything. Okay, that ends this segment.